This topic of photoelectric effect is also about quantization. When we talk about photons, it is like a packet of energy going in packets, quantized. So in that context, we need to look at the first evidence of quantum mechanics. You are looking at a graph which is plotted for the light that comes out from a hot object. The temperature can be 2000 Kelvin or 3000 Kelvin or 4000 Kelvin. I mean, one can draw this type of thing for a different temperature also. In this board you are seeing 3 temperatures that are considered. So you heat the object so much that it reaches that temperature. This is of course blackbody. And then you watch out for the light it emits. Light is a general term here. We are talking about electromagnetic radiation, whether visible to us or not. So when it emits light, you will find a mixture of wavelengths present in the light emitted. But there may be certain dominance. For example, we say that star is bluish side or something else. Now that does not mean that only that color is coming out from that star. We see sun has particular color, but what comes out from the sun has so many different frequencies, so many different wavelengths. So when it is hot, it is emitting large number of wavelengths or frequencies as far as electromagnetic radiation is concerned, but there may be some dominance. Some frequency could be dominating or some wavelength could be dominating. Here we are talking about wavelength. So this is intensity versus wavelength. For example, if you look at 4000 Kelvin, you find that little bit to the left of 1 micrometer, little bit to the left of 1 micrometer, there is a peak. That lambda may be 0.9 micrometer. That wavelength is dominating. There's a mixture of wavelengths present, but that wavelength is dominating. Likewise, at 3000 Kelvin, all types of wavelengths are present in the radiation which is coming out, but somewhere very close to 1 you will find the dominance of the wavelength. You would notice one thing, that if you increase temperature, lambda max goes to the left side. If you increase temperature, lambda max does not mean the maximum wavelength. Lambda max means the wavelength corresponding to maximum intensity. So if you increase temperature, lambda max goes to the left side. And if left side meaning falling, decrease, reduction in lambda max is taking place. If reduction is there in lambda max, it means the frequency is becoming more. So high temperature body, hotter body will radiate maximum for certain frequency which is on the higher side in comparison to a body at lower temperature. frequency will be higher side, lambda will be on the lower side. Lambda max is becoming lower for a hotter body, but frequency will be on the higher side. And high frequency generally means high energy. If we talk only about colors, then we can say that a body which is emitting blue color more must be hotter than a body which is emitting red color more, because blue color has higher frequency than the red color, or red color has higher wavelength than the blue color. Now, Max Planck realized that if he assumed energy of photon to be quantized and equal to h nu, then he could explain these graphs. And then Einstein used this equal to h nu for photoelectric effect, explaining photoelectric effect. And it was possible to explain photoelectric effect also. Here h is called Planck's constant. Okay, here comes a question. A series of light bulbs are colored red, yellow and blue. We are talking about the traditional incandescent type of bulb, right? Which bulb emits photons with most energy? What's your answer? Let's first talk about most energy. Most energy. Red means largest wavelength. So how does it become most energy? Largest wavelength means smallest frequency. So the answer should be blue. For most energy it should be blue. And what's the answer for least energy? Red is at the bottom for energy. Okay, which is hotter? Stove burner glowing red or stove burner glowing orange? Red is longer in wavelength, so orange should have higher energy. Orange should be correct. Any questions regarding these? Let me know. Suppose we are talking about traditional incandescent bulbs. All bulbs have got same wattage, but one is red, other is green, then blue. They are all having the same wattage. Then which bulb's filament is hottest? Yes, all wattage means same. So that color is due to the coating. That color is due to coating, not due to the filament temperature. So that is a different reason altogether, not related to the current discussion. Same is correct. Another question. Consider red beam and green beam, two beams, both having the same power, 2.5 milliwatts. Then in which beam more photons are coming every second? One photon corresponding to green will have less energy. So to have the same energy of 2.5 millijoules, more green photons will be required. Oh, just a moment, it is red and green. I was thinking blue and green. No, in that case, if it is red and green, then red photon has got lower energy. One photon corresponding to red has got lower energy, and you need 2.5 millijoules of energy. One fellow has less energy. So don't you need more fellows to reach the same energy level? So answer should be red. Any questions regarding this? If you have, then let me know. In that graph, you saw how lambda corresponding to maximum intensity was shifting. That lambda corresponding to maximum intensity is called lambda max, and lambda max into T is a constant. This is Wein's displacement law. T is in Kelvin. So from those graphs, Planck arrived at something very important, h nu. Then Einstein got Nobel Prize for photoelectric effect, which established that photon behavior is there in light. Otherwise, what is light? That was a long debate in those days. There were experiments which suggested that light must be waves like interference, and this experiment, photoelectric effect, could be explained only if you treat light as particle. So this experiment made people accept the particle behavior of light also, and then both had to be accepted, the wave behavior also and particle behavior also, because there were experiments supporting both behaviors, wave behavior also and particle behavior also. So photoelectric effect was not only useful in generating electrons from metals, in generating electrons from metals outside the metal. You are able to boil off, pull electrons out of the metal. That is photoelectric effect. And therefore you can have current. So not only due to that, which is very, very important, but also due to this fact that it established the particle theory of light. So what is the effect? Effect is that light incident on metal can pull electrons out of it. Now, electron just would not come out of the metal. Electron is floating in a sea of ions. Electrons are free, fine. I mean, not all, but many electrons are free. But they are still being pulled by the ions. Electron can be free to move within the metal, but going away from the metal is not easy. So ions try to pull electrons, and that has to be overcome. So some energy must be provided so that some electron can leave the metal completely. You are aware about power. Power is measured in watts. The light intensity is power per unit area. Say in a small room, there is 1000 watt of lamp. In a small room, there is a table, and 1000 watt of lamp is glowing. That means huge amount of energy is coming in unit area of that table. Now imagine the same bulb glowing in a hall in which there is a big table. Bulb is the same and the table is big. So in unit area, you are not able to get that much amount of energy every second. So intensity has to do with brightness. Now we have an experiment for this effect. What is that experiment? You have metal and you have some light source. You can change the light source. You can change its color. You can change the metal also. Different metals you can have. And there's the circuit, electrical circuit. Electrical circuit would not complete if electrons do not come out of the metal. Electrical circuit will only complete if electrons come out of the metal. So imagine an incomplete electric circuit. Batteries, battery, everything is there in that circuit, but there's a break in the circuit, break, and that break can be completed if electrons actually jump from one point to the other point. So imagine a circuit like this. It has got everything that you need except a break. There's a break here. And maybe that plate is here, metal plate. This could be some battery. Like this. There may be a resistor in the circuit to limit the current. There may be a switch. This is a plate. There is a clear break here. So unless electrons actually jump, you cannot have circuit. There is ammeter also. Ammeter will tell us how much current is flowing. Now, there is going to be zero reading, obviously, but if you throw light will come from here, and you find ammeter is showing reading, then it obviously means there is some effect called photoelectric effect, without which you could not complete the circuit. So experiments were performed, and the results of the experiments could not be explained from the wave theory of light. The results that came out from the experiment could not be explained from the wave theory, and they could be explained from the particle theory. So that established the particle behavior of light. And at this point of time, there is no doubt about it, because there is so much advancement. Say, for example, the wave behavior of electron, even that has been observed. So now wave particle duality is fully accepted, and it's not only valid for light. So what happens to the rate electrons are emitted? What happens to the current? If you increase the intensity, which means you increase the brightness, put a 40-watt bulb there, throwing photons, put a 100-watt bulb there, throwing photons, and watch out for the ammeter reading. This thing can be done experimentally. So, a lot of things were changed in the experimental setup, and observations were made. Another question could be, what happens to the maximum kinetic energy of the electron? When electron comes out of the metal, it may come out with almost negligible energy. With great difficulty, it just managed to come out. That could be one possibility. But other possibility could be that it comes out with very good amount of kinetic energy. And some electrons can come out with good amount of energy. Some electrons may come out with reduced or negligible amount of energy. Why? Because different electrons will follow different paths inside the metal from which they are trying to come out. The collisions that are possible for different electrons, different collisions are possible, different interactions are possible. So different electrons can come out with different kinetic energy. So let's focus on the maximum kinetic energy possible. Maximum kinetic energy means no collision. No collision. The electron just overcame the attraction, which is what we mean by work function. Attraction by the ions, etc. That has to be overcome. That is called work function. After work function, there could be collision. If there were no collisions, then the electron would have maximum possible kinetic energy. If there is one collision, less. Two collisions, even less. It would keep on decreasing that way. So, in increasing brightness, does it affect maximum kinetic energy? That could be another question. If we change the color of light, increasing the frequency, make it blue from red, what happens to rate electrons are emitted means currents? What happens to the emitter reading if you change the color of light from red to blue or whatever? Then effect of change in frequency to maximum kinetic energy. This is what the actual experiment tells. If you increase the brightness of the source, 40 watt bulb to 100 watt bulb or 1000 watt bulb, you throw its light on the metal. What happens to the current? It increases. Look at this. Kinetic energy, nothing happens. Nothing happens to kinetic energy. Whether you use a 1000 watt bulb or a 100 watt bulb. Now that's important because that's where the two theories differ. According to wave theory, energy can be absorbed continuously, gradually, you keep on absorbing energy. So if you keep on absorbing energy, then kinetic energy should increase. The fact is, it doesn't. What does particle theory say? Particle theory says that if you take 1000 watts or if you take 100 watts, as long as both are throwing blue color photon, one blue color photon has same energy. Yes, when you were throwing 1000 watt light, photons were too many, but one photon hits the electron. One photon hits the electron. It's not like wave theory that electron will keep absorbing and absorbing and absorbing. One photon will hit the electron. Whether that photon has come from 100 watt bulb or that photon has come from 1000 watt bulb. If both are having same color bulbs I'm talking about, both are throwing identical photons, then electron can absorb same amount of energy from one photon, whether it came from 100 watt bulb or 1000 watt bulb. So why should electron have different energy? So particle theory could explain the results, wave theory could not. Now, whether you take red color or blue color, electron can keep on absorbing according to the wave theory. So why should it matter whether it's red or blue? After all, over a period of time, electron can absorb energy from red also, blue also. according to the wave theory. So why should there be any difference in red and blue? Particle theory says something different. It says one photon will hit the electron. If it happens to be blue photon has got huge energy. Red photon has got less energy. If electron has got more energy, it can fight with metal better. After all, metal is not letting electron go. Otherwise, electron could come out from any metal. Electron otherwise could come out from any metal on its own. Metal doesn't let it go. So electron has to fight with the metal, work function that I was talking about. So if electron has absorbed a blue color photon, then electron has greater energy, it can fight the metal better and acquire its freedom in an easier way. So according to particle theory, if you make color change from red to blue, then current should increase. It does increase. Kinetic energy, same story. Wave theory says whether red or blue, over a period of time, absorption will be there gradually. So why should it make any difference, red or blue? Particle theory says that it's not about gradual absorption, it's about a bullet. It's like a bullet hitting. So photon hits. If it's a blue photon, well, it will give more energy to the electron. Electron has to fight with the metal. It loses some energy. But difference of the two is what kinetic energy is about, ignoring the collision. So if it gets more energy, it should be having greater kinetic energy also. So particle theory says, if you change from red to blue, kinetic energy should increase. Experiment says it does increase. So wave theory fails here. Particle theory is firmly established from this experiment. We stop now.